Hello, my name is Yassin Watson, and along with my wonderful teammates Sam Elwell, Julia Tepper, and Jordan Young, we are honored to present to you about our proposed mission to Titan. In the following few slides, I will be discussing the big picture, stakeholder perspectives and needs, and the current state of the art. Pictured on screen to the right is a composite image of Saturn's moon Titan. One of the most compelling things that has drawn the curiosity of people of various scientific and engineering backgrounds towards Saturn's moon is the presence of fundamental hydrocarbons like methane and ethane. These biomolecules may provide key insights into the origin of life itself. Furthermore, Titan is the second largest moon in our solar system, and in fact is the only such moon with substantial atmosphere, rivers, lakes, and oceans. Additionally, uneven fluctuations in its gravity field may suggest that a global internal ocean could lie within. This is all to say that, if successful, this mission will be the longest running probe on the surface of a celestial body in our outer solar system, in part due to the fact that Titan has a uniquely thick atmosphere, which can enable aircraft surveying. As mentioned, the study of hydrocarbons on Titan can enable advancement in a great variety of scientific disciplines, and as such, stakeholders will require clear imaging observation of celestial bodies, collection of physical samples, and ease of use and access to that collected data. Now, it should come as no surprise that deep space missions are considerably more complex than low Earth orbit missions, and due to the great distance between Titan and Earth, this will require a much larger launch vehicle, more complicated orbital maneuvers that could include flybys and gravity assist from other planets, increased cost, longer timelines, and overall added levels of uncertainty. To begin this process, we identified stakeholder needs, pictured on screen. These include a lot of the fundamentals of the mission, including launching the vehicle, getting into orbit, transferring to Titan, but also includes maintaining communications and data transfer with the ground station. Lastly, we also considered the launch timeline, remaining within program cost, and of course, complying with deep space mission standard documents. To get a better understanding of the current state of the art, let's take a look at some of the history of the exploration of the Saturn-Titan moon system. In 1979, NASA's Pioneer 11 made the first flyby of Saturn. And later on, NASA's Cassini made 124 flybys of Titan over the course of 13 years, beginning in 2004. This provided vast amounts of data for study, and in fact, Cassini's lander accomplished the first and only landing in the outer solar system in 2005. Now, this brings up some discussion about the difficulties in exploring Titan, which can include withstanding extreme temperatures during descent, and optimizing orbits of all planetary bodies between Earth and Titan. Additionally, orbital trajectories drive propellant needs, and thus the mass budget, the cost budget, and launch vehicle selection. With that said, advancements in public-private partnerships may reduce cost barriers to deep space exploration. For instance, collaboration between NASA, SpaceX, and Blue Origin has uncovered novel, reusable launch vehicles, including SpaceX's Falcon Heavy, which has the greatest commercially available payload capacity, as well as NASA's Space Launch System, pictured on the right, which is a new class of super heavy lift rockets.
Hi everyone, my name is Julia Tepper, and I will be defining the problem for our mission in the next few slides. Our mission is to develop a concept for a cruise stage to deliver the Asteria aircraft and associated Aether lander to Titan. Our mission begins at launch vehicle separation and will deliver the payloads to a target orbit around Titan before delivering the payloads for entry, descent, and landing, and will then remain in orbit around Titan to serve as a relay between the aircraft and the ground station on Earth. The primary goal of the mission is to safely and successfully deliver the Asteria and Aether payloads to Titan. However, the cruise stage will then be responsible for multiple other critical operations. The cruise stage will be responsible for attitude correction and maneuvers to maintain the correct trajectory to Titan. Additionally, the cruise stage will then need to maintain the payload during its transit and periodically health check the payload. The cruise stage will also need to receive commands and report telemetry. Upon reaching Titan, the cruise stage will deliver the payload to Titan in preparation for entry, descent, and landing. After delivering the payload, the cruise stage will remain in orbit around Titan for the duration of the mission and serve as a relay between Asteria and Earth. Naturally, this is an incredibly complex mission and comes with a set of constraints that guide and influence our design. First, Titan's over 1.5 billion kilometers away, and we will need to deliver a sizable payload. This introduces mass constraints due to the difficulty of reaching such a distant target. Additionally, since Titan, Saturn, and the Earth are constantly in orbit around the Sun, the trajectory needed to reach Titan is not static. Optimal planetary positions must be considered during launch, and this may constrain launch dates or potential flybys. Lastly, the development of this mission will take multiple years, and the cruise stage will take additional years as well. The large space vehicle will be considerably expensive. Budgetary constraints must be considered when developing the mission as well.
Hello everyone, my name is Sam Elwell, and in the next few slides I'm going to be taking us through our concept of operations, our functional decomposition, and our functional flow block diagrams. We chose to break our concept of operations down into two phases, the first being the transfer to the Titan system and the second being our operations around Titan. On this first slide here, you can see our 7-step process for transferring to the Titan system, including flybys and capture. On the second slide, you can see our operations around Titan that involve receiving data from the vehicle on Titan and transmitting that back to Earth. From a functional perspective, we've broken the mission down into 7 simple steps. Some are levied on the vehicle, such as getting there, communicating telemetry, releasing the payload, and then communicating scientific data and terminating the mission. But some are also levied on the team back on Earth, such as communicating the results and archiving those results. We've also defined our mission functions down to a level deeper in the form of a functional flow block diagram that defines all of the actions that the vehicle will take over the course of the mission. So here on this first slide, we have that defined for our transfer phase to Titan. And on this next slide, we have that defined for our general operations around Titan.
To build off of this work, we then conducted a quality functional deployment. As noted in the correlation matrix, we found it interesting that very few characteristics had negative trade-offs. In fact, a majority of our engineering characteristics had positive trade-offs between them. But notably, the negative trade-offs included maintaining a power-positive state as well as maintaining the vehicle within thermal operating limits. This makes sense because many typical operations will counteract one another, making accomplishment of these requirements a bit more difficult. Fortunately, a majority of the other engineering requirements had mostly positive correlations, and having positive correlations between these requirements will lead to fewer required trade-offs and a less complex solution.
Shifting our focus now to mission requirements, we can start by looking at our specification tree that just does a decomposition of our system level requirements and environment requirements down into the subsystem level. So looking first at our high level requirements, they've been defined in a SMART format, and I'm not going to go through all of them here, but the key takeaways are that they define our environments and the capabilities and functions that our vehicle will have to perform over the course of the mission. In addition to writing these top-level requirements, we've also put them into a SysML model so that we can visually show the relationship to the subsystem level requirements. So as you can see on this slide here, we have 3 boxes that highlight the different parts of those top-level requirements. So on this next slide, we show that first set. On this next slide, we show that middle set. And on this last slide, we show that rightmost set. At this top level, we've also done a system decomposition in SysML so that we can show a relationship between the different subsystems and the full system with specific values and functions so that we can run parametric models to get a better understanding of the overall vehicle and how it performs so that we can make better decisions. And that brings us to our subsystem requirements. So to do that, I wanted to start again with the specification tree just to show now that we're looking at that lower level set of requirements. But since there are so many requirements between all of the subsystems, we're not going to go through every single requirement. But what I wanted to point out is that these subsystem requirements have also been included in our SysML model. So as you can see on this slide here, we've got the 2 of those shown in blocks 1 and 2. And so on this first slide, you can see that decomposition for the first box, and then on the second slide you can see that for that second box that we looked at first.
Hello everyone, my name is Jordan Young, and I'm going to be presenting on the propulsion subsystem requirements, the 2 parametric models, which are the propulsion subsystem performance model and the system level mass model, and the propulsion method selection trait study. So these are the propulsion subsystem requirements. Much of this was derived from propulsion-related trade studies, and they are written in context with other cutting-edge real-world propulsion systems. And since electric propulsion was the chosen method, these align with that type. In these next few slides, we'll be discussing the parametric models. The first of these is the propulsion subsystem model. This was created to describe the propulsion subsystem performance. In particular, it relates to dry mass, wet mass, delta V requirements, and specific impulse. The main feature is the 3 constraint blocks, one of which calculates the total system dry mass. The other one calculates the propulsion performance using the classical rocket equation. And the third calculates the total mass of the propulsion subsystem for use in the system level mass model. So here in this figure, you can see the 3 parts as well as the constraint blocks. The next model is the system level mass model, which contains 2 summing blocks to sum the masses in both the dry and wet cases. And here you can see on the top the dry mass summing block and on the bottom the wet mass summing block, each of which takes inputs from either the wet or dry propulsion model.
This is the portion of our QFD that details the prioritization of each relevant metric, as well as the anticipated comparison to other relatable missions. The most important takeaways from this diagram are mainly the most important requirements, which are to maintain a power positive state and maintain control of the vehicle throughout the mission. Comparing the vehicle to other missions, you can see that our vehicle is expected to perform better for most requirements. When constructing our morphological matrix, we pulled many options from existing missions that have been proven to work. The 3 comparable missions we considered were Dragonfly, Cassini, and Perseverance. Considering the components that these missions used in addition to several more components allowed us to evaluate the most optimal choices to achieve each function within our design. These were the optimal selections for our mission. Each of the choices was selected due to being the most effective choice, and each component has a high technology readiness level as well as a heritage of successful past missions.
Now I'll be discussing the trade study that we performed. The propulsion subsystem was selected for the trade study, and the purpose was to determine what form of propulsion the system will use. The options under consideration were electric, liquid chemical, solid chemical, and nuclear, and the criteria that were being evaluated were efficiency, thrust, reliability, and cost. This was performed in the context of another smaller trade study in which we selected a trajectory. The trajectory is pictured in the bottom right. However, the study assumes that the launch vehicle will complete the first burn, which comes out to 6.27 kilometers per second, and that our system will be responsible for the remainder of the mission, which is about 3.5 kilometers per second, including margin. And on this slide, you can see a more blown up version of the trajectory. So for data gathering, we used a dry mass of 1,500 kilograms and a delta V of 3.5 kilometers per second. Below, for each propulsion system, specific impulse and dry masses were collected from various documentation, and the wet mass was calculated using the propulsion subsystem performance model. Finally, the results are pictured in the decision matrix below. In total, the electric propulsion won out by a slight margin, so that was the propulsion method that was selected. However, further study is necessary to determine just how large a factor thrust plays, and if an electric propulsion system would truly be able to provide sufficient thrust to execute the planned trajectory.
Verification and validation is one of the most important parts of a development cycle to ensure that the product is functioning as expected and needed. For each requirement, I developed a method of verification to ensure that the spacecraft is able to meet or exceed the requirement. A majority of the methods of verification are rigorous tests designed to quantitatively analyze the component. However, demonstration, analysis, and inspection methods were also used where appropriate to minimize cost. Lastly, these were the main risks to the mission that needed to be considered. For the most pressing risks, we also considered applicable mitigation efforts. In the following matrix, we ranked each risk by its probability of occurrence as well as its risk to the success of the mission. Ultimately, only one risk had a high-risk ranking, which was the potential for MMOD damage. Each of these risks was considered throughout the design of our mission to effectively mitigate and minimize these risks.
Thank you all for your time listening to our proposed mission to Titan.